Welcome to the deep dive. Think about your favorite online app. It's just always there, always working, right? Even when things are constantly changing behind the scenes. How does that actually happen? Well, today we're diving into a really key piece of that magic, Kubernetes Services. We spend time digging through, well, everything from architectural diagrams to, developer blogs, trying to boil it all down. Our mission here is to give you a real shortcut to understanding this foundational concept, so you can quickly get how applications in Kubernetes really connect.
Yeah, it's true. When you're starting out with Kubernetes, the networking part can feel pretty intimidating, like a maze. But services, they're kind of the thread that pulls you through. They make communication reliable, whether it's just inside the cluster or, talking to the outside world. We're going to try and simplify this. Think of a service almost like a permanent street address for your app. It routes traffic efficiently to the pods, even though those pods might be moving around or getting replaced all the time.
Okay, so if the challenge is managing apps that are always sort of shifting around, what is the fundamental Kubernetes answer? What exactly is a service?
Right. At its heart, a service is a Kubernetes resource, an object that gives you a stable, unchanging way to reach a group of pods. Something people maybe don't always realize is without services, every little change like a pod update or scaling up or down, that could break connections between your apps. They'd constantly have to figure out new IP addresses. So services are Kubernetes' really elegant fix for that constantly moving target.
That makes a lot of sense for stability. But what other big problems do they solve? It's not just about the fixed address, is it?
No, not at all. Beyond just having that stable endpoint for those ephemeral pods, they handle load balancing automatically. And this isn't just about, spreading requests evenly. It makes your application resilient, like really resilient. Imagine 1,000 users hit your web server pod. Kubernetes sees that, spins up 10 more pods maybe, and the service just starts sending traffic to the new ones instantly. Users see nothing, no lag.
Ah, okay. So it smooths out those peaks and valleys.
Exactly. Then there's service discovery. This is huge. Apps can find each other just using simple DNS names inside the cluster. No more hard-coding IP addresses, which is just brittle.
Right. That sounds much cleaner.
Definitely. And finally, flexibility. Services support different ways of accessing things, purely internal chat between microservices or, opening things up to the public internet.
Okay, just to quickly recap some basics for context. We're talking about pods, right? The smallest thing you deploy, one or more containers.
Yeah.
They all live in a Kubernetes cluster, a set of machines. And we usually interact using kubectl, the command line tool.
Right.
The API server is kind of the brain, processing all the configurations. And critically for services, you mentioned labels and selectors. That's how they know which pods to send traffic to.
Precisely. That's the magic connection. The service uses selectors to find pods with matching labels. Doesn't matter what their IP is or which node they're on. So given these different problems services solve, it makes sense. Kubernetes offers, different types of services. Each one is really tailored for a specific job. We should dig into the three main ones you'll encounter: ClusterIP, NodePort, and LoadBalancer.
Okay, let's start with the default, the one you get if you don't specify anything else, ClusterIP. So its purpose is purely internal, right? A stable IP address within the cluster.
Exactly. It's for communication inside the cluster boundaries only. Nothing external can reach it directly. The mechanism is it creates a virtual IP. Think of it like an internal extension number that only works within the company phone system.
Okay.
And there's this component, kubeproxy, running on every node. It acts like the internal switchboard operator. It knows how to route calls to that virtual IP to an actual healthy pod that can answer, even if pods are starting or stopping.
So the real benefit of ClusterIP is secure, reliable internal communication. Perfect for microservices chatting with each other.
Spot on. Keeps internal traffic internal. No accidental exposure. It's the workhorse for back-end communication. Okay, building on top of that, we have NodePort. This one does allow external access. Its purpose is to expose your service on a specific port, but on the IP address of every single node in your cluster.
Wait, on every node? How does that work?
Yeah, it sounds a bit weird at first. Kubernetes picks a high-numbered port, usually somewhere between 30,000 and 32767, and opens that same port on all your nodes. So imagine your cluster has 3 nodes, traffic hitting node 1.30000, node 2.3000, or node 3.30000, all gets forwarded internally to your service and then onto the pods.
Ah, I see. So you could hit any node's IP on that specific port and reach the service.
Exactly. So why would you use this? It's Pretty simple way to get external traffic into your cluster for like testing or development, maybe when you don't have a fancy cloud load balancer set up.
Okay, makes sense for quick access during dev.
Yeah, it's not usually recommended for production, mainly because you have to manage which node IP you're pointing at and what happens if that node goes down, but it's useful.
Right. Which brings us to the load balancer type. This sounds like the production-ready solution.
It generally is, especially in cloud environments. Its purpose is to expose a service externally using a cloud provider's native load balancer. This gives you a single, stable, external IP address.
So this actually talks to the cloud provider, like AWS or Google Cloud.
Precisely. The mechanism involves Kubernetes integrating directly with the cloud platform's API. When you create a service of type load balancer, Kubernetes tells your cloud provider, hey, provision an external load balancer for me and point it at these nodes or pods. The cloud provider does its thing, gives you back an IP address, and handles distributing traffic to your nodes, which then route it via kubeproxy to your pods.
And the big win here is
Simplicity and robustness. You get a proper managed load balancer without configuring it manually. It handles health checks, scaling, provides that single point of access. Ideal for customer-facing applications needing high availability. So even though these three types, ClusterIP, NodePort, load balancer, expose things differently, they share some core mechanics underneath.
right, you mentioned some already.
Yeah, label selectors are fundamental. Every service uses them to know which pods are part of its group. That link is crucial. Then there's kubeproxy. It's running on every single node, watching the API server for changes to services and endpoints, and constantly updating the network rules like IPtables or IPVS to route traffic correctly.
So kubeproxy is the unsung hero making the routing happen on each machine.
Pretty much, yeah. And the other key piece is DNS. Kubernetes automatically gives each service a DNS name, like my-service.default.svc.cluster.local. Applications within the cluster can just use this name. They don't need to know the cluster IP. The internal DNS resolves it for them. It's like a built-in phone book for your services.
That internal DNS is super useful. Okay, let's make this concrete. Can you walk through some real-world scenarios for each type?
Sure. For ClusterIP, a classic example is a web front end needing to talk to a back-end user authentication service, both running in the same cluster. The front-end code just references the back-end using its service name, like auth service. Kubernetes DNS resolves that to the cluster IP, and kubeproxy routes the request. All internal, all secure.
Okay, simple enough. What about NodePort in practice?
Right, NodePort. Imagine you're a developer, you've just built a new version of a web app, deployed it to your dev cluster, you want to quickly check it in your browser, you create a NodePort service, Kubernetes gives you port 30123, say, you find the IP address of one of your cluster nodes, put http.nodeip.30123 in your browser, and boom, you see your app. Quick and dirty testing.
Gotcha. Easy way to poke it from the outside temporarily.
Exactly, and then for load balancer.
The e-commerce example.
Yeah, that's perfect. Think of a big online store. They need a single, reliable web address for customers worldwide. They deploy their web server pods, create a service of type load balancer. Their cloud provider, AWS, Azure, GCP, provisions an external load balancer with a permanent IP. All customer traffic hits that load balancer IP, which then intelligently distributes it across all the healthy web server pods, scaling up or down as needed. That ensures the site stays up and responsive during, say, a big sale.
Okay, that clarifies the when and why for each type. Now, how does this all fit together with the rest of Kubernetes? You write the YAML, but what's the sequence of events?
Right. So you, the user, define the service in a YAML file. You specify the APIT version, kind, service, some metadata like the name, and then the important spec. In the spec, you define the type, cluster IP, NodePort, or load balancer. The selector define the pods and the ports.
And you submit that YAML using kubectl apply-your-service.yaml.
Yep. That sends it to the API server. The API server validates it, stores it in, etc., the cluster's database. Then the Kubernetes service controller sees this new service object. It creates a necessary endpoint allocating a cluster IP or reserving node ports. Almost simultaneously, kubeproxy on each node sees the new service and its associated pods via endpoints or endpoint slices and updates the local network rules. It programs the routes.
So the routing rules get pushed out everywhere.
Correct. And remember, pod assignment is dynamic. If a pod matching the selector starts or stops, kubeproxy gets updated and adjusts the routing rules automatically. Now, if it's a load balancer type, there's an extra step. The Cloud Controller Manager, a component that knows how to talk to your specific cloud provider, sees the request. It then makes API calls to AWS, Google Cloud, or wherever to provision that external load balancer resource.
And you, the user, just monitor it.
Yeah, you can use kubectl get service to see the assigned IPs, ClusterIP, external IP, and kubectl describe service for more details, check events, make sure everything looks healthy.
So boiling it down, why are services so effective? What are the big wins?
I'd say four main things. First, stability. They give you that fixed address, decoupling clients from pod IPs. That's foundational. Second, load balancing. Built-in distribution of traffic for resilience and scale. Super important. Third, flexibility. The different types cover internal, testing, and external production use cases really well. And fourth, automation. Kubernetes handles the endpoint management, the network rule updates, the cloud integration. It takes away a ton of manual network config hassle.
It really feels like Kubernetes' way of taming the complexity of distributed systems networking.
That's a good way to put it, yeah.
Okay, let's wrap up with some best practices. If someone's working with services, what should they keep in mind?
Good idea. First, be precise with your label selectors. Make sure they match only the pods you intend. Loose selectors can cause, well, unexpected traffic routing.
Good point. Target carefully.
Second, choose the right service type for the job. Don't use NodePort in production if you can use LoadBalancer. Use ClusterIP whenever you don't need external access. Keep things as locked down as necessary.
Makes sense. Principal least privilege, network style.
Exactly. Third, monitor connectivity. Use probes, check metrics. Just because a service exists doesn't mean traffic is flowing correctly. Verify. Fourth, definitely leverage the internal DNS for service-to-service communication inside the cluster. Avoid hard-coding cluster IPs. Use the service name.
Much more maintainable.
Way more. And finally, a simple but crucial one. Keep your service YAML definitions in Git or some version control system. Treat your infrastructure configuration like code. It helps with tracking changes, rollbacks, collaboration.
Absolutely essential advice. So understanding these service types, ClusterIP for internal, NodePort for simple external access or testing, and load balancer for robust external exposure, it really is crucial, isn't it?
It absolutely is. There are the building blocks that make sure your application components can actually find and talk to each other reliably, whether they're hidden away inside the cluster or need to face the outside world.
They're the glue holding it together.
You could say that. Now, here's something to think about. You've seen how Kubernetes abstracts away a lot of the low-level network complexity with services. So how does that change the game for you when you're designing applications? What new possibilities does this open up for building really resilient, adaptable architectures? Especially if you're thinking about maybe running across different clouds or hybrid environments. Consider how this abstraction lets you focus more on your app's actual business logic and less on, the plumbing underneath. What does that freedom enable?